Section 5.4 is strangely titled, What Do Forces Do? And I will give away the punchline. It's got something to do with proportionality. Really what he's introducing in this section is the concept of mass. So, we agree that there's a something which has a vector nature that we can call a force, okay? And we can sense it. When you push on something, you sense it in your hand, that it's pushing back on you. It's pressuring the pad of your hand. And if it could sense, it would sense that you are pushing on it. So there's a force of it, the board, on you, your hand, and there's a force of you, your hand, on it, the board. So there's even two forces there. We have to agree at this point that there is such a thing called a force, that it is a vector. What we discover is that if you have a force and you push on something, so I'm going to imagine that, say, I've got a block here, okay? This is a block. And I push on it. Well, the amazing thing is not just that it changes its position or it gives it a velocity. The amazing thing is it turns out that there's a direct relationship between how much you push on it and how much it accelerates. That's why we work so hard in chapters 1 to 4 of bringing out this notion of acceleration, because what forces do is they cause acceleration. And furthermore, they cause acceleration in a very quantitative and simple way, okay? So if I put a certain amount of force on this block right here, and if I stack a second block here, which has all the same properties as the first block, then I will find that instead of getting the original acceleration, now that I've got two blocks here, I'll get whatever the original acceleration was divided by 2. Or, to put it a different way, this whole idea of proportionality, suppose I push my hand on the back of this block, and then suppose I put my other hand beside this hand, and with both hands I push the same amount on the back of this block. Well, we discovered that it's another proportionality, that if it was with just one hand it was A, then with two hands, each pushing the same amount as I was originally pushing with just one hand, we have A 2 hands is 2A 1 hand. In other words, to be a little more precise about that, or a little less colloquial about that, if I double the force, I double the acceleration. And to put the other one a little bit more in an equation fashion, if I double the mass, but keeping the force the same, so I'm just doing one hand, if I double the mass, I get half the acceleration than I got with the original mass. So this is leading up to a proportionality statement. If I triple the mass, obviously I get 1/3. If I quadruple the mass, and I've got 4 blocks here, then I get 1/4 the acceleration. And the way we capture that here is we say there's this new thing, m, called the mass. And the relationship between the force and the mass is proportional. So if I have 4 times the mass here, but the same force, I must get 1/4 the acceleration. So if this goes up by 4x and this stays the same, this must go down by 4x. This is an increase of mass of 4 times. This is a decrease of acceleration of 4 times. You can construct an endless number of examples. If I double the force but keep the mass the same, then A is going to have to double in this equation. So this section, 5.4, is introducing the idea that there is this proportionality constant between force and acceleration, and we call it mass. So since we have this new thing that we've discovered, and it's certainly not length and it's not time, it's mass, it's a new thing. We've already got MKS units for length, that's meters. We've already got MKS units for time, that's S. So we've got meters, we've got seconds. The new unit is the MKS system for mass is kilograms. So we're going to introduce the idea of the kilogram. It's a little weird to have 1,000 of something as the fundamental unit in a system, but that's the way it is. In the MKS system, the fundamental unit of mass is the kilogram, not the gram. Now, so let's just kind of look at this proportionality again now that we've got a name for the unit of mass. Let's say we've got an equation that's F sub x is equal to the mass times A sub x. That's the x component of the full equation. F sub x is the mass times A sub x. Well, this here has units meters per second squared. And this here, we just agreed, has units kilograms. So the right-hand side of this equation has the units of kilograms, meters per second squared. That combination comes up so much in these kinds of equations, kilograms times meters times second squared. That combination comes up so much that we give it its own name. This combination is called the Newton, like in Fig. The Newton, and it's abbreviated capital N. Now, while I'm going through abbreviations here, I want to clarify something that might seem like a little bit of an annoying inconsistency, okay? It's pretty hard when you have mass, which is very often labeled M in these problems, and meters, which is very often abbreviated M in these problems. It can be a little bit of an annoyance to keep them straight. I'll tell you, in a textbook like Knight, a variable like mass is generally done in kind of a cursive or script font, and a unit like M is done in a little bit more of an old school typewriter style font. On the whiteboard, there's no easy way for me to make a distinction between M for mass and M for meters. So you'll just have to stay on your toes and figure out whether or not I'm doing a unit or a variable. That's Knight 5.4. The only thing he adds is some more nice graphs and discussion of the idea of proportionality, including when something is inversely proportional to another thing. So if you have this equation like this, that fx is equal to max, you can rearrange this equation. So then it could be ax is equal to 1 over m fx. Well, now instead of looking like it's proportional to m, it's proportional to 1 over m, and we call that inversely proportional. So the other thing Knight adds here, which you'll want to take a look at, is how the graph for a situation where something is inversely proportional to something else looks. We're ready for 5.5.